Section 4.1. Today we are going to do differential equations. Now, what are differential equations? It's something that when you solve for y, normally we do a function like y equal to f of x, and but the different and equals to something, right? And we solve for y or something like that. But in in a differential equation, the difference is that there's y, and then the derivative of y are in the same equation, and you're supposed to somehow make it come out. And as an example, let's look at the next page where you have a bunch of differential equations that as examples. Now, for example, the first differential equation is just, there is no y in there, just y prime, so that's slightly easier to do. But look at this, let's see the third one. Okay, look at the third equation where you have y double prime, that's the second derivative, and y prime, that's the first derivative, and then y itself, and all equal to something, and you have to come up with what y might be, and that's why it's called a differential equations. You have derivatives within the equation, you have to somehow decode it, and that sounds kind of hard, and it is. However, we're going to start out with doing something super simple to get us going. Now, example 4.1, you are supposed to verify the solution of the differential equation. That is, in this case, we're supposed to verify that the solution. Okay, the solution is already given to you right now because we're just starting out so that you get a feel for it. Now, can you see it carefully? Okay, see, it's just in your book. You don't have to read it. Look at the screen. Now, see the solution, y equals to e to the power minus 3x, etc. I mean, that function is a solution to that differential equation on the other side, where you have y prime and 3y and all that stuff. And your job in this problem example is to verify that to be true. And how would you verify that? Well, there's only one way to verify it. You take the derivative of y, and then you multiply, then add 3y, and see if it equals to the other side, 6x plus 1. Or if there are more y's on the other side, you plug that in too and see if the equation holds. If it holds, then that y is the solution of the problem, just like you do verify any other solutions. So that's a bit of grunt work, okay, but it's nothing that you haven't done before. So please do example 4.1 as part of your homework. Next, let's look at some definition at the bottom of the page where it says the order of a differential equation is, what is the order? The order is just the highest power derivative of of the differential equation that you're looking at. For example, we have previously we have looked at some samples of differential equations. This is back on the top of the page where the first equation, the order is 1, I believe, and then the third equation, the order is 2, because the highest order is the second derivative. So that's all that means. It doesn't mean a whole lot, but you should know what the word means. And so for that, please do example 4.2 where you identify the order. Next, let's look at the general and particular solutions. Because derivatives, when you take derivatives of something and then you come back to the original solution, that's integration. Now, in integration, as you remember, there is often some constant c. That is because two functions that are within something within some constant c will have the same derivative, okay, because the derivative of constant is 0. And therefore, for that reason and maybe some similar reason, a differential equation will have the general solutions and particular solution. The general solution is everything within that c, you have a plus c, similar to integration at the indefinite integral, whereas a particular solution is when you have it gives you a specific information so that you can pinpoint which c do we want. And so that's the only difference. Now, for example, and for that, please do example 4.3, which is just a repeat of what you've done before. But this is to give you a feel of the differential equation. Although it's similar to integration, there is a lot harder and more involved because the derivative or even the second derivative and the y are all in the same equation. So things become, a much bigger headache, let's just say. So please do example 4.3 as your homework. Next, let's think about the initial value problems. That's not different from the particular solution, I don't think. What happens is that once there are certain conditions you might have that will nail down what that C is, and that's what you're doing right here. But in example 4.4, again, you're going to be verifying that some function is the solution of the derivative plus it satisfies the condition that when t is 0, y equals to 3. So again, you're just verifying. So please go ahead and verify it and get the feel of the land, so to speak. So please do example what is this, 4.4 as part of your homework. And lastly, in this section, we're gonna solve a differential equation. However, this differential equation is something that you can handle because it's the same as the good old integration problem, because it's an extremely easy one. Okay, you don't even have y in there, just y prime. So y prime, which is a derivative, so dy by dx equals to a bunch of stuff, and then when x is 0, y equal to 5. I'm looking at example 4.5. Okay, now when you look at this problem, you should know how to solve it. Okay, I mean, look at this. How would you solve it anyway? Well, you integrate both sides and then plug in when x is 0, y is 5, and to solve for your c, right? So please do this example, even though it's a bit of a grunt work to set yourself up, because things get a lot tougher from this point on. So please do example 4.5 also as part of your homework. And that gets us to the end of this section. The book also talks about the falling object problem, which we happen to have done it in Calculus 1, the early part. And so we're not going to waste time repeating that, and just get on to, I'll assign a few homework problems, and then we're going to move on to section 4.2 when we're going to do actual differential equations. So for homework for this section, which is on page 362, please do problems 9, 19, 33, and 39. And that should be good enough for anybody. And with that, let's move on to the next section. So next, let's look at the next section, section 4.2, where we're going to do something called directional fields, also called force field. Slope fields, sorry. Yeah, that the calculator calls it a slope field. Before I forget, I should mention that there's a calculator that plots the slope field for you, so you don't have to do it by hand if you don't want to. Now, and you might not want to for the following reasons. So first, let's talk about what is it. Well, let's say you have some kind of a thing, right? Okay, you have. Let's look at the following page, 366, where there's a figure 4.7, where we have a slope field. Okay, and the slope field represents the differential equation that's called let's see, y prime equal to 3x plus 2y minus 4. That is fine, but what does the slope field mean? The slope field means that you're going to draw an x and y, okay, and that's the plane, right? So here's your x and here's your y, and then we'll figure out something. What are we figuring out? Figure out each point on the slope field and draw the slope. For example, let's start with origin, of course. 0, 0. When x and y are 0, the slope is -4, okay? And what's the negative slope for slope? It's something like maybe like this, right? I'm just drawing the slope here, okay? The slope looks something like that, not the length of the line itself, just the slope. And then what happens when the slope is, let's say, 1, 0, x equal to 1, y equal to 0, that would be -1, right? -1 is not as slanted, okay, as you can see in your book. So -1 is maybe like that, right? And then let's pick another point. Maybe y, let's see, x equal to 0, y equal to 1. How about that? If x is 0, then y is 1, then the slope is -2, okay? Which is not as slanted as -4, but minus 2 is still somewhat slanted, so I'll do my best to draw it. And you continue to do this, okay, until you come up with the entire slope field like your book shows. See, that's your slope field. Is my camera focusing? Come on, focus. Yeah, I think it doesn't like the red color. Doesn't matter. You can just look at your book. The point is, you continue to do this for the entire plane. And after, I don't know how long it will take to do this. I have never tried it. Maybe I haven't tried it. I don't remember. But I'm the kind who avoid this type of grunt work. And you can see where this is going, right? There's a reason that differential equations back in my day are sometimes called the difficult equations, because you're going to be drawing this. But don't panic yet. Things are not that bad for you. Well, partly because you have something called the slope field or directional field generator. You just type in this equation, and the decimal calculator, which the link I have set down below the video, is going to do all this stuff for you, and it'll look fantastic. Now notice that the slope field has arrows. The purpose of the arrow is just to remind you that the slope goes this way. It always goes from left to right. Doesn't matter how slanted it is. For example, if a slope is like this, then it must go this direction. If the slope like that, then it must go that direction. It always goes from left to right, because functions only go from left to right. You're not going to have a function that turn backwards. Doesn't work that way. So that's why there are arrows on it. Okay. So what the slope field does is to give you an impression of the function. Okay, the function, well, at least the impression of what the slope is, what y prime is at each point of your graph. And so you're looking at this thing, and you kind of can imagine it as maybe the wind blowing. The wind is, in this case, the wind is blowing down right over here, and it's blowing, I don't know, it turns here and blows back up, and then over here sort of blow down, and so on. And how does, okay, which that doesn't solve the equation for you, but it gives you a feel, let's just say, of what this function sort of look like. Okay, and that's what a direction field is. And okay, well, that's fine. And what are we going to do with it? So let's look at the next page and figure out what is there to do. Now, the way to use the directional field is something like this. And let's go to page 367. Let's say the directional field passes through a certain point, like x equals to 0 and y equals to 1, like here. Then you follow, so then you eyeball it, as the Americans put it. That is, you estimate from this point based on how the field is going. As you can see, how is the field going? I will quickly draw in how the field is going. Somewhere like this. Okay, the field is going down here and sort of going slanted here, and then kind of turning here or something. Anyway, so you eyeball it from here and look at where the field is going. Imagining it's like the direction of the wind, and let yourself get blown, as you're estimating, something like that. And then down here, the wind is blowing, I don't know, like this, right? And like this and something, and so you figure down here is probably something like this, and that you estimate that's sort of your solution for y, if y goes through 0, 1, and that's an initial value problem, similar to integration, that if you have a point, as we have done earlier, then you can calculate, you can figure out what this constant c is, and then give you an exact solution. So here's my estimate of the solution. As you can see, it is not particularly impressive, so here you are, made it all the way to calculus, and you have gotten into differential equations, and what are you doing? You're eyeballing something. And that does sound kind of depressing, but there is good news in the horizon. We're not actually going to do any eyeballing. Okay, so let's go to the next part. So next, let's look at page 368. There's an example here for the differential equation where y prime equals to this stuff. Okay, and you notice that in here, there's something in here that such the solution for this thing is y. So one solution would be y equal to let's see which one the book. Okay, y plus 2, or this. So let's consider y equal to -2, which is what your book is considering. Now, if the equation y equal to -2 is just a straight line, right, below the x-axis. Now, if y equals to -2, then y prime is equal to 0. Okay? However, that's on this side of the equation. Furthermore, if y equals to -2, this side of the equation is also 0. Therefore, y equals to -2 is a solution to this problem. And similarly, y equals to +2 is also a solution. Okay. Now, if you are to plot this thing out on the directional field in the calculator or by hand, hopefully you don't have to do it by hand, but you might want to do it by hand just for the fun of it, see what it looks like. But anyway, if you were to plot it out as your book shows, you notice that there are the y equals to -2 and y equals to +2 are straight lines. That's because they're the solutions, and furthermore, they're just everything's straight. Now, if that is the case, then it is called such a solution where y equal to a constant has a name for it, and it's called the equilibrium solution. Now, the equilibrium solution has an interesting quality in that they might attract or repulse something. That is, I mean, look at the function, how the arrows are going, right? On top, the top equilibrium solution, that's y equals to +2. Then see, all the arrows are pointing towards it, right? So the solutions that go for it will likely be attracted to the equilibrium solution, well, for as long as the other arrows are pointing towards it. Okay, towards the end there, the arrow's pointing again, so they're taking a hike. Whereas the solution down here, you see, all the other arrows are pointing away, which means if you start at a slightly different point, you very likely will get taken off, and so that basically that equation sort of repulses solution. Other solutions tend to get away from it. So let's look at the next page. So there are names for these things. That is, if solutions get attracted to an equilibrium, and then it's called the asymptotically stable solution. Okay, everything likes to gather together. It's popular. And on the other hand, if solution tends to be repulsed by it, it's extremely unpopular. It's called asymptotically unstable solution. Now, if neither fact is true, it's just sort of not really attracting or not attracting anybody, then it's called the asymptotically semi-stable solution. Actually, let's just call it stable, unstable, or semi-stable. Let's not say the other word because it's kind of hard. Now, in example 4.8, you're supposed to identify the equilibrium solution, whether it is stable, unstable, or semi-stable. So please do that as your homework, example 4.8. And with that, we will move on to Euler's method. Now, as I've mentioned before, to figure out from this directional field which way your function solution is going, then you can eyeball it, starting from the initial point and eyeball it, judging by which way the slope is going. Now that, of course, is incredibly imprecise, and we're not going to do that in calculus, right? So then what are we going to do? We're going to do it with a scientific method, something that actually makes sense. And this method is designed by Euler, who is, I might as well tell you that now, he is the greatest mathematician of all time. Okay, and even though he's not that famous. So Euler's method, it says that we have some kind of a function, right? To demonstrate Euler's method, we're going to use a very simple example to which we do know what the solution is. Okay, and the reason why are we doing something we already know the answer to is to check Euler's method to see how good it is. Right? Because how would you know if the method works if you at least confirm that it works pretty good? So we'll confirm it with something that we already know the answer to test the method. So what does the method do? Let's look at the next page. Give me a second. Now let's look at page 372. We have some kind of a simple differential equation here, and we're not going to care about the solution for now. Okay, there is the condition, the initial condition, which determines what the constant is. So, but what we're going to do is solve it with the Euler's method. Now, Euler's method is clever and yet direct. That is, it is a fairly ingenious way of doing things by using the directional field but not eyeballing. Okay, so here we're going to do is first y, when x is 0, y is 3, so we start here. That's our function. And the next thing we're going to do is take a step. The step that we're going to take is 0.5. So the step size for this, for now, we'll choose a step equal to 0.5, which means we're going to move over 0.5, okay, where x is now 0. X started at 0, we're going to move over to 0.5 to and then figure out what the slope is when at and at that point, before we move over, we'll figure out what the slope is here, which when x is 0, y is just like the directional field, right? When x is 0, y will be -3. The slope, of course, is negative 3. But we're going to go over here, okay? So from -3, we're going to draw a straight line that is the slope of -3. So the slope here is -3. Slope. Let me write it down. Slope equal to -3 for this point, right? So we're going to draw that thing all the way until we get when x is 0.5. In other words, we're going to follow this line and draw the equation for this thing. What is the equation? You use the point slope formula and you will come up with the equation, right? And we're not going to do that right now, but we know that we have an equation. So we're not just drawing eyeballing. We're actually doing it by equation. And so this is an exact line with a slope -3, which is the slope at that point, and of the differential equation. And we're going to draw it precisely until it stops at 0.5. And at that point, we're going to repeat the process. And when x is 0.5, and well, wherever this point is, okay, being that this is a precise line, we can figure out what y value is by the line, right? Because we know the equation of the line. So from that point on, we know what this point is. This is not the original solution, but it's an approximation. So this is called, let's call this y1, whatever it might be. Actually, I think your book did calculate it. Yeah, we're not gonna. Well, it's 1.7 or something. We don't care. And so once we calculate y1 from this line that we calculated, we're going to repeat the process and figure out what the slope here is. Okay, plug in x equal to 0.5 right here, and then it gives you some other slope, right? And with that, you're going to come up with the point slope formula, draw another line. So you draw another line, the step is 0.5 now, so the next step is 1, so you get here. And you continue this process, which means you're no longer eyeballing. You have a systematic method of keep going to follow the directional field. See, you're doing the same thing here, except you are precise and exact, and you are using the slope at each point of the directional field, and then using the point slope formula to draw your line and figure out exactly where the point is for the next one. So that's not going to give you the exact answer, right? Because you're using a straight line to approximate something that might have a curve in it. But it will give you a nice approximation, especially when you're close to the original point. The closer you are, probably the more likely you're going to be right. So when you do all that, one step at a time, you are going to have this. This is called the Euler's method. Okay. Now, the top beautiful curve, the smooth curve, is the actual answer. The bottom the stepping, what do you call that thing? That's not a curve. It's just a bunch of straight lines joined together. That is the Euler's method approximation. As you can see, it's not amazing, but it does look pretty good. And if you don't know what the answer is, I mean, it beats the heck out of the eyeballing, right? So that's why this solution is so neat. However, if you think about it, each tiny little step, you're gonna come up, use the point slope formula, you're gonna draw an equation of the other line, you have to figure out what the next y is. All that sounds like a giant headache, tons of grunt work, which is true. However, as you can imagine, nowadays with our modern technology, there's something called the Euler's method graphing calculator, which will do all the stuff for you if you just type in the formula like what you want graphed. And I have the link below the video. So I did a sample of it. What is that? I think that's exactly what the book has. Okay, so you just type in the formula, and you can type in the initial spot. Where do you want to get started? And then you even type in the step size. See down there, and it's the step size, which is how much you want to go out each time. And see the decimals. What is this thing called? This thing called the Euler's method. I don't know what it's called. The name I wrote down might not be accurate. I might not have made that up. But the point is, it's the Euler's method something. And the link is down there, and you can draw this thing out without lifting a finger. Ugh, I don't like lifting fingers. Just there's no grunt work for doing Euler's method now. How awesome is that? And just think about in the old days when Euler designed this thing, he didn't have the graphing calculator. He has to do all this by hand. He didn't even have the calculator to figure out what the slope is. He has to do that by hand. I'm pretty sure there was no calculator in his day. I could be wrong. I hope I'm wrong about that, because the poor guy has to do each and everything by hand. Ugh, that would be yeah, that would be, like your head's gonna explode. But we don't have to do any of that. So that's why we can use calculus as a hobby, right? We don't have to do all that grunt work. But you, of course, if you like doing that sort of thing, do a whole bunch of stuff by hand, or if you don't have access for this calculator for some reason, then feel free to do it by hand. There's nothing wrong with that. It's just I'm just lazy and don't like to do any more work than I have to. So but you don't have to, be like me. Learn the good, not the bad. Anyway, so that's Euler's method, and as you can see, it's totally awesome, right? Because we have a calculator that does it. So no more eyeballing. So you just started eyeballing, and we're done. Because I would not want to be eyeballing in calculus. So then, yeah. Anyway, so the official statement of the Euler's method on the next page, theorem 4.1, whatever page this is, doesn't matter. It summarizes what I just said. So what you do is you have a bunch of x's, which is defined by the step, and then you have a bunch of y's, which is a bunch of lines. Okay, all these lines that you come up with by the point slope formula, which they already did for you, so you don't have to do the formula. You just reinvent the formula. You just plug it back in. See, you just here's your formula where and the slope is f of xy. In this case, for each n, okay, on your step, right? Oops, sorry. Okay, try again. All right. So then, so x is just a bunch of stuff, whereas y is y is the whole bunch of slopes. You plug it in and you draw the line and so on, but that is just so much better. Yeah, the lines are not going to have neat answers like 5. You're going to have a bunch of decimal points most likely. And but once you get that, then you have a bunch of neat answers. Let's see what's going on. Okay, give me a second here. I should mention that the Euler's method, as you can see, you go a step out, right? So if your step is closer, the answer gets more, the approximation gets better. Okay, it makes sense that the closer you approximate, the better it is. But as the farther you get out, however, the more likely your answer is going to take, wander off somewhere else. But still is far superior than the eyeballing method. So on the following page, page 374, then you can see the effects of a smaller step. See, this is the bigger step, 0.5 or something. And the other one's the smaller step, about half that much, 0.25. And as you can see, the smaller step does a much better job, but of course the smaller step means you have to do twice the work. So that's that's that. So please try to use the Euler's method, and you can use it with or without the calculator on example 4.9. and that's the only example we have to do. Now you can use the calculator with a link. The graphics calculator Euler's method thing that I will have a link below the video. Or you can, if that's not available, or if you want to do exactly what the book does, but without doing the actual work, you can also do something, do this thing on the spreadsheet. Of course, the spreadsheet can only give you the numbers. It's not going to plot anything out. Okay, so here's the spreadsheet, the Google Sheets that I used to do this solution. I will show you this thing. Can you see it? Some of the colors seems odd. Okay, that's pretty good. All right, that's a D. That orange color is not showing up very well, but that's a D. I think you can see it okay. Okay, that's the first formula. Okay, I am so as you can see, you can do the Euler's method on the Google Sheets too. No problem. The detail, I want to show it to you so that you know it can be done. And that's the example of the formula to show you how it has to be typed in. It has to be typed in exactly, including the multiplication and all those things, because it's Google Sheets, right? It's not a math program, it's an accounting thing. So once you type it in, then everything else will fall out. The rest of the information, if you don't know how to use spreadsheet, you just drag it along the corner, the blue dot on the other side, and you click your mouse and push it down and drag it all the way out, and everything will come out like that. Okay, I only typed in the first 2 lines or so. All the rest is dragged out. So if you don't know how to use Google Sheets, please figure out how to do it. Even if you don't use it for this, it's a good idea to know how to use Google Sheets on a fundamental level. In other words, there's a lot of Google Sheets. I don't even know what all is in there. But just spend about 5 minutes to know how to use it for mathematical reasons, which is very basic. How do I type in the formula in Google Sheets, and how do I make it work? That kind of thing is very, very handy to have. Even if you're not completely required, by now you should know the basics of how to use Google Sheets to, among other things, balance your checkbook. Okay, it's much nicer than, I hope you're not typing the numbers in by hand still. Now that we got Google Sheets available and it's free, right? So that's that, in case you want to do that. Okay, I think that's about it, right? Is there anything else? I think that's the last example, and then we're going to do homework. So for homework, which is on page 377, section 4.2, please do problems 67, 69, 71, 73, 77, 85, 87, 89, 91, 93, 97, 101. 111. Now, that sounds like a lot of homework, but it's not. This is still an introductory chapter section, so the problems are all like very, very short. Well, maybe not all, but most of them. Okay, you're just looking at field and you eyeball the answer or something like that. I'll figure out which one is the equilibrium. What was it called? Whatever it's called is quick. Okay, because the problems are very direct, very straightforward, I will not be talking about them because I don't think you need it. Just get the homework done, and then we'll move on to the next section when we're going to solve differential equations by hand and get the exact solution, not just use approximations, which is Euler's method. Now, it's just like integration. Differential equations, sometimes you can solve the exact equation, but a lot of times you can't. And like integration, there is no way to do it, which is why we have Euler's method. Euler's method is good for, especially if you can't do it, right? The normal way, but we'll go to the next section and figure out how to do at least some of the easier problems, relatively speaking, how to solve this thing and get the exact solution, not just an approximation.